For this class of Data Communications and Network 1, this is on Lecture 19, Chapter 10, Local Area Network, Part 1. Okay. This chapter will be about the overview of the local area network, or LAN, L-A-N, LAN. Okay? LAN is traditionally a broadcast network. A broadcast network means that everyone can get the information or everyone receive the transmission from everyone else. Like I'm broadcasting right now, I'm taping the video, right? So it's like I'm broadcasting to you. So anyone who want to receive it, okay, can click on the YouTube and then get the information. So this is kind of the broadcasting, or what you have heard about like television broadcasting, okay? So everyone can get the information. So local network is that way, okay? When you send something, everyone else in the network can get the information if they want, okay? So since everyone get the information, there is no need for the routing, okay? So you don't have to like go from this node to that node to those nodes, okay? You don't have to do that because whatever you send out, everyone receive it, including your destination, okay? So there's no switching and routing. Now let's look at the topologies of LAN. The first one is bus LAN. This is the one that is used the most, okay? Bus topology is like we have like a bus, okay, or a line. That is like the medium, okay? Then you have the computer or the user, okay, tap from the line. So you have the line here, okay, and then you have like computer tapping from the line, okay, like as you see in the picture there. And at the end of the bus, okay, of the line, you have a resistance, okay. This is like absorbing the resistance to absorb the signal that is transmitted until it reaches the end, okay, so that it will not echo back into the line. Okay, so that it will not get interfere with the signal that is transmitting at that time. Okay. So we have what we call like a tap. Okay, in the when it like the computer or the station tapped to the media. Okay, or the line on the bus. Okay, and then when you want to transmit, okay, the transmission from a station, suppose in the middle station here, in the middle one, okay, when you transmit, you send out both ways, okay? So the signal go out to the left and to the right. So everyone on the left and on the right can get the signal, okay? And you don't need to do the routing, but you have to put address of the destination, okay, on the packet, okay, that you are transmitting out, so that the intended receiver will know that this is the packet, so that they will make a copy of it. Because if it is not the station that is not the intended receiver, when they look at the packet, okay, they look at it. Suppose this is like the header of the packet, okay, and it see, okay, this is not my address, okay. What happens is that they will just pass this packet through, okay. It will not make a copy of the data of this packet, okay. So other station, which is not the receiver, look at the address. This is not for me. It will just send the data. Just send the packet along, okay, without making any copies. Okay, and this cannot be for very long distance because you see that there is a bus, right? There's a bus. So the signal, when you transmit through a bus, the signal power go down, right? So at first it have a high power and then the power go down with distance. So you cannot make it very long distance. So the signal strength will be too low to detect, okay, if you use it for too long distance. So this is kind of the local area network, okay. Now let's look at if C want to send to A. C put the destination of the destination address A on the packet here, and C send both on the left and on the right, okay. But this one we consider only on the left, okay, because A is on the left. So this one go to A, go past B. B look at it. It's not addressed to B, so B ignores it, okay. Then it go to A, okay. Then A see that this is for A, okay? So it's make a copy, and then it leaves the packet, original packet to go still along the line, okay? Now the only transmission media that are widely used for bus topology is baseband coaxial cable, okay? But right now for bus, there are more and more. Originally, okay, it was used with baseband coaxial cable, but right now they have like high-speed Ethernet, okay, which is also use the bus topology, okay. So they will have the more media, okay, like fiber optics and you know other media to use on the Ethernet, which use the bus topology too. Now the baseband coaxial cable is, as I said, is used in the Ethernet system, okay, which is IEEE 802.3. And an example of the baseband IEEE 802.3 LAN are the 10 base 5. The first number, okay, number 10 means that it's 10 megabit per second, okay? And base is for baseband transmission. 5 is 500 meters cable length, okay? So when you look at this 10 base 5, okay, standard, it means 10 megabit per second baseband transmission and 500 meters cable length, okay? We call this thick Ethernet, okay? There will be another chapter on the Ethernet exclusively, because Ethernet is the technique for LAN, okay, that we use the most now. Anyway, this is the basic Ethernet. This one called thick Ethernet because it's used 0.4 inches inch diameter coaxial cable, okay? The second one is the 10 base 2 or 10 megabit per second baseband 200 meters cable length. So the first number is the same, but the last number is different, okay? So the number 2 here is the 200 meters cable length. We call this thin Ethernet, okay? Because it's used a diameter, smaller diameter, okay, of 2.5 inches diameter coaxial cable. If you want to use transmit for longer than 200 meters or 500 meters, then you can use a repeater, okay, to join two segments of the cable together. So you can see that this is one segment, okay, of the bus or of the Ethernet, and this is another segment of the Ethernet, okay, the vertical line. This is also another segment of the Ethernet. So we have 3 segments here, two horizontal line and 1 vertical line. They are connected with a repeater here, okay, near the end of the line, okay. So you can see that this one is connected like this. So this is one repeater, and this circle is another repeater, okay. Now, the user or the station can be connected from any of the segment, okay, and it's still the same bus LAN, okay. And the repeater is transparent to the rest of the network. It means that the user here, it will not know that there are many segments, okay. It will think that it's the same line, okay, or the same media of the bus LAN, because when this guy transmitted, okay, it will go on the left and on the right. When it goes to the repeater will make it like clearer, okay, with a more signal strength, and send it to connected to here, right, to this segment. So you transmit on this segment. So the computer in this the second segment, okay, will just see the signal or the packet coming, okay, without knowing where it comes from, okay. I mean, it doesn't know that it's on another segment. It's just think that the transmitter is in the same bus LAN, which is correct. The next one is three LANs, okay. This is the next topology. In this case, it's like you have many buses connected together with a head end, okay. So you have, again, you have for each line, you have station, okay, tapping from the line, but they are combined together at the head end, okay. So they are combined together at the head end here, okay. Now the three LANs are LANs, okay, with 3 topologies, okay. This is generalization of the bus topology. So it can have many branches, okay. but the bias topology has only one branch, okay? But you cannot have any closed loop. If you have a closed loop, it will have a problem, okay? It will have a problem of that it will get confused. It will get confused, okay, of the signal that have been received. Okay, so for tree land, you cannot have a closed loop. Okay, so it's called tree. If it have a closed loop, it will be a ring lands. Okay, so it will be a different topology. Okay, so if what I was saying about the if there is a closed loop, okay, and you may have a problems, okay, if you use the same technique, okay, so different topology you may have different techniques. You will see it in the ring lands later, okay, in the next one. Now for bus and tree, okay, there are no need to concern about removing frames from the cables, okay, because frame will be absorbed at the head end, okay, or at the end by the terminating resistance. But if there is a loop, okay, which is a ring, okay, we call it a ring land, so you have 4 stations here, or maybe more stations, okay, connected into a loop, okay, and at each of the when the station connect, it will connect with a repeater, okay, so you have 4 repeaters here with 4 stations, and it will run this way, okay. I'm not sure because it's kind of opposite. Anyway, so this run clockwise, okay, in this case. So each of the repeater, okay, will receive and then regenerate and retransmit each bit one by one sequentially. So when you send a frame or packet, okay, it's actually, usually we call this a frame, okay, at this level. So a frame consists of many bits, right? So the repeater, okay, we received a bit and then regenerate, okay, retransmit it onto the line, okay, until it's complete with one frame, okay. This is a unidirectional link. The unidirectional means that it goes only one way, okay. So the data circulate, okay, in this case it circulate clockwise, and there are 2 ways to remove the frame, okay. You can have source removal or the destination removal. If it's a source removal, it means that the station who sent the frame, okay, is the one, when it go complete the circle, okay, it will remove it, okay. And if it's destination removal, it's that when it reaches the destination will be the one who removes the frame, because there is no use to send further, okay, because it's already reached the destination. So you can see here, the first one, okay, you can see that C want to send to A, right? So C put A as a destination, okay. If this is the okay, anyway, C put A as a destination, then this one is counterclockwise. Anyway, it has to be unidirectional, but this example is counterclockwise in this land. So it's go to B, then B saw that it is not for B, okay, it's for other user. So it's just leave the frame, okay, to go along the line. A look at it, okay, A know that it is for A, okay, so A will make a copy, okay, and then leave the packet to go along, okay. Then when it reach C, okay, complete the circle, then C remove the frame, okay. The frame is usually in this layer, okay, packet is in the upper layer, but people usually call it, and even myself, okay, like interchangeably. Anyway, so this frame, okay, C will take it, okay, so this is source removal. But if A absorb, okay, take the frame, okay, and do not send to C, then it's called destination removal. So if this one, C is a source, if C remove it, like in this picture, it's source removal. If A is a destination, if A remove it, okay, and do not send further to C, it will become destination removal. Anyway, so you can see that if it's a closed loop, they will have to have a technique, okay, to not make the frame, okay, run indefinitely, okay. But if it's a tree or a bus, then you have a terminating resistance at the end anyway to absorb the frame or the signals, okay. The next one is star LAN. This is a next topology. For the star topology, you have a central hub, okay, or a switch or a repeater, okay, at the center, and then you have many users, okay, connected to the hub. So every user connected directly to the hub. So you have two directional transmission, okay. So user send to the hub send to the user, okay. And with this topology, the line in between that connect between the two, the hub and the users, okay, it can also be wireless. So you can have a hub here, and you can have like, this would be wireless, okay, transmission. Okay, so for wireless LAN, okay, we use star topology, okay, because this is suitable for wireless LAN, okay, because we can just change this one to wireless link, okay, instead of wire media. Now there are two approaches for the operation of the central hub, okay, or the central node or the hub, okay. We can do it broadcasting. If we do broadcasting, okay, when a station sends a transmission to the central hub, suppose this one send signal, okay, send to the hub. Okay, the hub will broadcast to everyone, okay, to all stations. So the hub will broadcast. This is broadcasting. So this is one way you can do broadcasting. Another way is that you can do switching. For switching, if in this it say go to B is the destination, then you will just send the hub will just switch it to B, okay, only. So this is called switching. Switching means that you just send to the correct destination, but broadcasting means that you send to everyone in the network, okay. As I say, the topology when it's used in the wireless LAN, okay, is good, okay, and we can use radio frequencies instead of cable to connect the stations and the hub together. Next, we will talk about the LAN protocol architecture, okay. In this case, we look at the layers, okay, the layers architecture, and comparing the layer architectures of the network that use LAN with the OSI reference model. So there are several standards of IEEE standard for LANs, okay. Usually we call it in general, okay, collectively as IEEE 802. And when it does something, it's like different LANs, okay. For example, if 802.3, this is CSMACD or the Ethernet, okay. And IEEE 802.4, this is token bus, okay. I think you know the Ethernet, right? Ethernet. This one is CSMACD. Ethernet is like a common name. CSMACD is like the techniques, okay? The techniques that we use. This is IEEE 802.3, okay? And this is the most used standard in LANs nowadays, okay? Now, what is the IEEE stand for? It's the Institute of Electrical and Electronics Engineers, okay? Okay, now let's compare the layers, okay, the layers architecture. For the OSI model, we have the 7 layers, okay, physical layer up to the application layers. For the 802 reference model, we define the data link layer, okay, as we divide it into the medium access control layer, and the logical link control layer. Okay, so this is the scope of the 802 standards. It's just medium up to the LLC. Okay, the medium access control is MAC, MAC. LLC is logical link control. So this is the scope of the standard. Okay, which is basically up to the data link layer of the OSI model. So we define from the medium up to there. Now, all the LAN standards have the same LLC layers, okay? And they will be different in the physical layer and the MAC layer. MAC layer is the medium access control layers, okay? Now let's look at the relationship, okay, between each layer of the protocol architecture. If we use TCP/IP protocol, okay, when from the application layers, okay, we add the TCP header, and we will call this one TCP segment, okay. So application layer, we will put TCP header. We call this TCP segment. Okay, there are many names to call a block of, a block of packet or a block of data. So this is called TCP segment. When you put IP header on, it will call IP datagram. Okay, then you put LLC header on, it will call LLC protocol data unit or LLC PDU. Let's look over here. Can you see? If you put header, when you go to the TCP header, add TCP header at the TCP level, it's TCP segment. When you add the IP header, it's become IP datagram. Okay, it's just a different name. Okay, at different layer. And when you add the LLC header, it's become LLC protocol data unit. Okay, then you add the MAC header. You see the MAC in the MAC layer we have add both the header and the tailors. Okay, as the same as when we do in the data link layer, the normal data link layer. So we call this MAC frames. Okay, so in the LAN we usually call it a frame. What is MAC? Okay, what does MAC do? Okay, in this layer we control the access of the medium. Okay, because LAN has a big problem, a multi-access problem. It have to overcome this problem. The multi-access problem means that many users want to transmit at the same time. Okay, so but because LAN is broadcasting, so when one person speak, okay, as I'm speaking, or there are one user transmitting, okay, it means that all other users will hear, okay, that transmission. So if another user transmit at the same time, it will collide with each other. The signal will collide with each other, and no one will understand what is going on. And therefore, we have to prevent more than one user speaking at the same time, okay, or more than one user transmitting at the same time. So we have to control, we have to overcome this multi-access problem. Okay, so there are many standards, okay, for medium access control techniques. The first one is round robin. Okay, round robin means that it just go in turn. Okay, everyone get the chance in turn. This is a complete control of the medium access. So you control it 100%. This one is used in a token bus, the IEEE 802.4, the token ring, which is 802.5, the FDDI, which is the fiber distributed data interface. Okay, FDDI is another standard of LAN. Anyway, so this one, each station is given an opportunity to transmit the data in turn. So you have to wait your turn to transmit, okay? So it's very efficient if you have a lot of stations and the stations have a data to send, okay, for a relatively long time. So it want to keep sending. So if you have a lot of people like want to speak at the same time, you have to allow them, okay, you allow them to speak in turn, okay? And then when maybe like 5 minutes each, and when you are finished with the 10 people, then you come back again. The first one can speak another 5 minutes, something like that. So if a lot of people want almost all of them want to speak. Okay, this is good. But if only one person want to speak, only the first one want to speak, but the rest doesn't want to speak, this is not good. Because when the first one speak for 5 minutes, or the first user, okay, transmit for one frame, okay, it have to wait. Ask the second one, do you want to send? Okay, the second one say, no, I don't want to send. Then ask the third one, do you want to send? No, I don't want to send. Ask the fourth one, okay, until ask the last one. No, I don't want to send, okay, then go back to the first one again. So the one who want to send will have to wait for a long time. So this is not efficient if only a few stations have data to send, but it will be very efficient if a lot of stations want to transmit the data and want to transmit a lot of data, okay. The second one is called reservation. This is a lower, okay, degree, not 100%, but still high degree of medium access control. This is used in 802.6 or DQ, which is DQDB, distributed queue dual bus. In this case, the time in the medium is divided into time slot. And if you want to transmit a station that want to transmit, okay, we have to make a reservation in the future time slot. Okay, so this is good for stream traffic, okay, which is long and very continuous. You think of the reservation as when you want to eat a dinner, okay, at a fancy restaurant, and you have to make a reservation beforehand. Let me show you the frame here. So basically, you have this one is okay, is to make the reservation. Okay, and this one is the data. This one is to make reservation. Okay, so suppose A want to transmit, okay? A have to make a reservation first. Suppose A put it here, and B also want, D also want to transmit, okay? D put it here, okay? D is here, A is here, okay? So then, after you make the reservation, okay, and it's approved, okay, this is data A, this is data D, something like this, okay, you can transmit. Okay, and then you have to make a reservation again. Okay, something like this. It's like you book the time, okay. The idea is like you booking the time to transmit, okay. So you book, okay, I will use that slot, something like that, okay. So this is still high degree of medium access control. This is 100% is a round robin. This is how much you control the medium, okay, medium access control. And this is like reservation, okay. It's around here, okay. The next one is called contention. Contention is around here. Okay, and this is like aloha. No, 0% is like aloha. Okay, now let's look at the contention and aloha. Actually, the contention is, aloha is kind of included in the contention, okay, but this one is like CSMA CD, okay. This is what I'm saying, that still some control, okay, but no control is like aloha. Now let's look at the contention, okay. So in this case, you have some control, okay, for CSMA CD and CSMA, but no control for aloha. Aloha is not an abbreviation, okay. CSMA is carrier sense multiple access, and CD is collision detection, okay. But aloha is not an abbreviation. It starts in Hawaii, in the Hawaii Island. So this is kind of the greeting, hello, in Hawaii, okay. So for contention, we use in the IEEE 802.11, which is CSMA, and 802.3, which is CSMA CD. This one is good for bursted traffic, okay, which means that you send short, sporadic transmission. So you send, and then you have nothing to send for a long time, and then send again for a short burst, and then have nothing to send for a long time. Okay, so we will have many users, but most of them send for a short time, and then idle for a long time. So this is good for to use the contention, and it's turned out that Ethernet, okay, that use CSMA CD is the most popular, okay, of the LAN right now. So I will talk about contention, okay, in detail, but the other we just briefly talked about, okay, already, okay, and you can search more if you want, but we'll talk about the Ethernet and Aloha in more detail, okay. So this is simple, okay, the contention is simple because there's no control or who want to send at a given time. If you want to send, okay, you can send. So there are two techniques. If it's Aloha, no control at all. So if you want to send, you just send out anytime, and then you observe, okay, whether there is a collision or not. So in Aloha, if I want to send, my friends want to send, another user want to send, if I want to send, I just send, okay, I don't check anything. I just send out, and then I hear, okay, I listen whether other signal come in and then collide with my signal or not. If there's a collision, then I will have to send again, something like that. So that's Aloha. So that works if there are there are few users to transmit, okay, and the user send for a very short time of the, and idle for a long time, okay. In this case, we will send the channel first, okay. If the channel is available, this one is CSMA, okay. CSMA will carry sense multiple access, okay. This one sends the channel. So listen to the channel if someone is transmitting or not. If the channel is available, which means that no one is transmitting, then it will send the data out, okay. But if the channel is not available, it will wait until the channels become available. So this one will reduce the chance of the collision, okay. Really a lot of chance for collision. The next topic we'll talk about is bridge, okay. So Ethernet will be another chapter, okay, in more detail. Bridge is a device that used to connect two or more LANs together, okay, and bridge is transparent to the station in the LAN that it connects, which means that the LAN doesn't know that there is a bridge, okay. It's just connect to the user in another LAN, okay, without knowing that there are something between. We just think that it's the same LAN. So the bridge, okay, need to have buffer, okay, so that it will have to keep the frame before retransmitting. Now let's look at this picture, the bridge operation, okay. The bridge has to do routing, okay. So if you have LAN A and LAN B, and LAN A sends something, okay, send some frame, okay, and it will put the destination address on. If the destination address is from 11 to 20, okay, it means that this is in LAN B, okay. In this case, the bridge, okay, read the destination address. Oh, it's LAN is the user is in LAN B, so it will receive, it will take that frame, okay, and then transmit it out to LAN B, okay. But station 1 LAN A doesn't have to know. Maybe station 2 want to send to station 12. Station 2 doesn't have to know that station 12 is not in the same LAN, okay. The bridge will just take the frame and send it out to the correct LAN. Now if station 15 want to send to station 10, then the bridge also read the frame, okay, and destination is in LAN B, okay, but destination sender is in LAN B, but destination is in LAN A. If you accept the frame, and it will transmit to LAN A, okay, so that everyone on LAN A will see it, okay. So if it's in the same LAN, the bridge doesn't have to do anything, okay. So it's not the same as a repeater that repeat everything. The bridge will do some routing. Now let's look at the operation of a bridge, okay. The bridge will read all frames, okay, transmitted on A and accept those addressed to station on B. Okay, so if it's still in the same LAN, it doesn't have to do anything, okay. and it have to use the MAC protocol for B, okay, to retransmit to frame B. So if you have two LANs, okay, with different MAC protocol, then the bridge will change the protocol, the MAC protocol to so that it have to convert the MAC protocol so that station on LAN B can understand what it is, okay, and it's do the same, okay, for traffic from LAN B to LAN A. So this is a function of the bridge, okay. You can see that for this one, A send to B, okay, A send to D, station D just go directly, no use of the bridge. The second case, A send to G, go past a bridge. Now let's look at the bridge protocol architecture. Okay, in this case, look at there are two LANs, okay, on the left and on the right. The sender, their user data, okay, going down until consider at the data link layer. So they have a LLC layer and MAC layer, and then the physical layer. So at time T1, T2, and T3. Okay, so this frame go to the first LAN. At time T1, okay, the frame will look like this. The packet will look like this, time T1. Just the user data, okay. When it go past LLC, at time T2, okay, it will be LLC header with the user data. So this become LLC protocol data unit, okay. Then it go to MAC at time T3. Then you add the header and the tailer. So it become the MAC frame, okay, over here. Then it go to LAN, okay, go to the physical medium and go to LAN. Then it will go to you see that at time T4, okay, it still look the same, okay, the frame looks the same as a MAC frame, but it's sent in terms of physical signal, okay. Then go to the bridge, okay. The bridge has a physical layer and a MAC layer. So at the physical layer, okay, so no problem, let's go to the MAC layer. The MAC layer, it will strip out, okay, strip out it will strip out if it have to convert, okay, the MAC protocol, it will take out the original MAC header and MAC tailer. It will take out and then put in the new protocol of LAN B, okay. So if you have LAN A transmitting and then LAN B receiving, user is in LAN B, then the bridge will take the header and the tailer of the MAC, okay, of LAN A out, okay, and then put the header and tailer of LAN B in if they use different protocol, okay. So at T5, the same, okay, still the MAC frame in the physical layer, and go to the next LAN at the destination. Then the destination is connected to this LAN, okay. At T6, it's still the MAC frame, right? At T7, take the header out, okay, become the LLC protocol data unit, okay, and then go to at T8, go to the user. So this is the operation, okay, of the bridge, okay, that it function at the MAC level, okay, and keep the same LLC protocol data unit. If you use the same MAC and LLC, okay, the bridge just operate like this. The bridge just operate this way, okay, no problem. So that's the end of part A. For part 1, okay, we will continue about LAN on part 2 in the next video. Thank you.